Hello there, Mr. Sutton here, bringing you the AB Calculus 6-1 Extra Practice Number 1 solutions on differential equations in one variable. For this problem, we want the general differential solution to this differential equation. So for that, all we have to do is actually just take the antiderivative. So we have y on the left, and on the right, using the reverse power rule, this bumps up to an x squared. Dividing by 2, we just have 1 over there. So we've got x squared plus, using the reverse line rule, this is going to be 2x. Don't forget the plus c. On this one, we want the general solution to this differential equation. So we're going to take the antiderivative of both sides. On the left side, that gives us a y. On the right side, this is going to be negative 2 ln absolute value of x and plus c. And we also have to take into account what's happening with this absolute value. Since they told us x is less than 0, negative, that means we have to rewrite this as parentheses negative x, just so we're not taking the ln of negative numbers. So this is going to end up being our final answer for this one. On this problem, I want the general solution to this differential equation. So taking the antiderivative of both sides of the equation, we have y on the left. On the right, this is going to be 3 ln absolute value of 9 minus x, but because we have this minus x, we have to divide by the inner derivative of negative 1. So this is going to be negative 3 ln absolute value of 9 minus x. And don't forget the plus c. Now, since x is positive, or actually, since x is greater than 9, that means that I'm subtracting something bigger than 9 from itself. So if I'm doing 9 minus something bigger than 9, this stuff in here, 9 minus x, is actually going to come out negative. That means I need to reverse the signs in here in order to ensure that I get positive numbers. So I'm going to negate both of these things and basically write this as either negative 9 plus x or x minus 9. Either of those would do the job. And there we are. On this problem, I want the particular solution to this differential equation with the initial condition over here. So I'll start by taking the antiderivative of the original. That's going to be y equals 3 ln absolute value of x plus c. And now to get a particular solution, I'm going to have to plug in my initial condition here. So for y, I'm going to substitute this 3 ln of 3 minus 1 stuff. And then for x, I'm actually plugging in this 3 right here. So let's see here. I've got a 3 ln of 3 over here. I've got another one over here. To get c by itself, I just subtract 3 ln of 3 from both sides. That's going to cancel those out and leave me with just c equaling negative 1. So now rewriting this stuff up here, I also have to resolve this absolute value. So if x is 3, then that means x is positive. So that means I'm taking the absolute value of a positive, which is kind of a waste of an absolute value. So we don't actually have to write absolute value anymore. We can just write this as y equals 3 ln of x with no absolute value. And then don't forget the c value, which is now negative 1. For this one, I want the particular solution to this differential equation with this weird-looking initial condition. Let me start by taking the antiderivative of both sides. So that's going to be y equals, this is going to be 3 sine of x plus c. And now plugging in my initial condition, I've got the y value of negative 3 halves. And I've got 3 sine of pi over 6 plus c. What is the sine of pi over 6? Well, that's really the sine of 30 degrees, which is 1/2. So this is really 3 halves. If I subtract 3 halves over here to get c by itself, I have negative 6 over 2, which is just negative 3. So c has a value of negative 3 then. And then just plugging that back in, we have y equals 3 sine of x minus 3. On this problem, they're asking which of these equations y equals 2e to the 6x minus 5 is a particular solution for. Well, to say that this is the solution to one of these equations basically means when I plug this in, when I plug in 2e to the 6x minus 5 for y, and whatever the derivative of that is for y prime, it should make the equation come out true. So we see here that we have a few of these different equations. We're going to need to know what y prime looks like in order to test this out in some of these. Some of these also have a y double prime. Now, before I go ahead and find y double prime, let me just start with y prime, because that's going to be enough to test out this first equation. And if that doesn't work, and if choice B doesn't work, then I'll figure out what y double prime is and try out these other two. So y prime then is going to be, let's see here, we have 2e to the 6x times a tail of 6. So that's going to be 12e to the 6x, and then that 5 is a constant, so that's gone. So that's y prime. So now testing out choice A, let me plug in 12e to the 6x for y prime, and then 2e to the 6x minus 5 for y. So I've got 12e to the 6x right there. And then I'm going to subtract 6 times this 2e to the 6x minus 5 business. I still have a minus 30, and hopefully that all equals 0 when all is said and done. So let's start simplifying here. This is algebra at this point. So we still have 12e to the 6x minus 12e to the 6x plus 30 if I distribute. And then we had the minus 30 and the equals 0. So these e to the 6x terms are going to cancel. So are the 30s. So that does come out the same on both sides. So that shows that this equation is indeed a particular solution for choice A. And that means just the nature of these multiple choice questions, it's not going to work for anything else. So let's pick choice A. For this problem, we're being asked which of these is a solution to this differential equation. They didn't give us an initial condition or anything like that, and honestly, even if they did, this is going to be kind of tricky to try to figure out an antiderivative for. So when all else fails, if you're wondering if something is a solution to a differential equation, you just need to plug it into the differential equation. Now, plugging in is a little tricky here. We know what y equals for each of these, and there's a y that we would plug all that stuff in for. But we're also going to need to know what y prime is in order to plug things into this differential equation. So we're going to figure out y prime for each of these and plug it in along with the original equation, and we're just going to see what makes this thing work out. So for choice A, y prime here is just going to be 2x. So plugging that in with the original to the differential equation, we have x times the y prime that we just came up with of 2x, minus 2 times the original equation, x squared minus 2. And does all that equal 2? Well, it's algebra at this point. We've got 2x squared minus 2x squared plus 4. And does all that equal 2? 2x squareds are going to cancel. 4 does not equal 2. So this is a no. And we move on to the next one. For choice B, the y prime is going to be 2x plus 2. Plugging that in along with the original, we have x times parentheses 2x plus 2 minus 2 times that original function of 2x squared plus 2x. And let's see what all this comes out to. So we've got 2x squared plus 2x minus 2x squared minus 4x equals 2. 2x squareds, they're not right next to each other, but they still cancel out. And we have a 2x minus a 4x giving us a negative 2x. Does negative 2x equal 2? Well, it could for certain x values, but not for all x values. So since this is not true for all x values, it's not true enough to count here, so this is going to be a no. And moving on now to this one, derivative here, y prime is going to be 8x. Plugging that in, we've got x times 8x minus 2 times the original 4x squared minus 1. And that should equal 2. This is going to be 8x squared minus 8x squared plus 2 equals 2. 8x squareds are gone, and we just end up with 2 equals 2, which is true for all values of x. It's just true. So this is a yes. This is going to be the answer we pick in a moment, but we've already come so far, so why not just test this last one just to really have peace of mind on this. So for this last one, y prime is going to be 6x squared. Plugging that in, we've got x times 6x squared minus 2 times the original, which is 2x cubed minus 1, equals 2. So we've got 6x cubed, and this is going to be minus 4x cubed plus 2 equals 2. So we end up with 2x cubed plus 2 equals 2. And since this is not going to be true for all x values, I mean, it's true for 0, but that's about it. This is not going to be true enough to solve that differential equation, so that's a no. So then choice C, after all, is our answer. On this problem, we want to know which of these three options are solutions to this differential equation. Since we don't have the techniques needed to solve this kind of differential equation at this level of calculus, we're going to go to the fallback. When all else fails, just plug in your possible particular solutions and see which ones make this come out true. Of course, plugging these in, we already know what y equals, but in order to really plug things in here, we need to know what y prime and y double prime are. So y prime for this first one might as well start somewhere. This is going to be 2e to the 2t. And y double prime, because we're going to need that as well, that's going to be 4e to the 2t. So that could have been worse. Let's go ahead and plug all that in now. So we've got y double prime, which is this 4e to the 4t, minus 5 times this y prime here, 2e to the 2t times 5. And then we have plus 6 times the original, 6 times e to the 2t, equals 0. So doing a little algebra here, we've got 4 minus 10e to the 2t plus 6e to the 2t. And let's see here, this is going to be negative 6e to the 2t plus 6e to the 2t comes out to 0. So we end up with 0 equals 0, which is a true statement. So this is going to be a yes for option number 1. So any answer choice that doesn't have option 1 in it immediately can be eliminated. So we've already narrowed it down to choices A and D. And I mean, just being kind of sneaky with these problems, since it's between A and D and neither of those has 3 included in it, if you're really in a rush, you don't really need to test option 3 here because you know it's not in one of the answers that's remaining. Let's go on to choice 2 then, option 2. So y prime for this one is going to be 9e to the 3t. And then y double prime, we've got 27e to the 3t, using the chain rule this whole time. Plugging all that into our differential equation, that's 27e to the 3t minus 5 times 9e to the 3t plus 6 times the original, which was 3e to the 3t. So this is 27e to the 3t minus 45e to the 3t plus 18e to the 3t equals 0. 27 minus 45 is going to be negative 18 e to the 3t plus 18e to the 3t comes out to 0. So we've got 0 equals 0 again, also a true statement, so that's a yes. So it's looking like D is the answer here, but just in case we're curious, let's try option 3 and see what happens. So with option 3, our first derivative is going to be 6 cosine of 2t, and then y double prime is going to be, let's see, negative 12 sine of 2t. Plugging all that in, we've got negative 12 sine of 2t minus 5 times 6 cosine of 2t plus 6 times 3 sine of 2t equals 0. So let's see, this is negative 12 sine of 2t minus 30 cosine of 2t plus 18 sine of 2t. And there's the other one. And let's see, if I have a negative 12 and a plus 18, that's going to give me positive 6 sine of 2t. That's where that's coming from. So, yeah, this minus this, these aren't even like terms. You're not going to get 0 out of that for all t values. So that's a no. So that means that only options 1 and 2 worked, which is going to give us choice D. On this one, we want to know of these here, which is not a solution to this differential equation. So if you want to figure out whether or not something's a solution to a differential equation without directly solving the differential equation, you can just take the possible answer, the candidate we'll call it, and plug it into the differential equation to see if it makes it come out true. But in order to plug things into this differential equation, which has a y double prime, you're going to need to figure out y double prime of these options over here. So let's start with option A. That's definitely the easiest out of all these. If y is 0, then y prime is, well, also 0. So is y double prime. So is y, like, all prime. So those all come out to 0. And I don't know why I put a y triple prime in there. That seems a little excessive. Certainly not wrong, but we don't need it for this problem. So let's go ahead and plug all that in. So we have y double prime, which was 0. Minus 9 times y, which was also 0. And does all that equal 0? Well, yeah, 0 minus 0 does come out to 0. So this is not the answer we were looking for because they said which is not a solution to the differential equation. So I'm going to put a yes here, but by yes I mean yes, this comes out true, and no, it's not the one we want. So yes means no in this particular problem. So on to the next one. Y prime for this is going to be, let's see here, we have a chain rule going on. So this is going to be 3 cosine of 3t. And then we need y double prime, another chain rule, so that's going to be negative 9 sine of 3t. Plugging all that in, we have negative 9 sine of 3t for that y double prime, minus 9 times sine of 3t equals 0. So this is, let's see, negative 9 minus another 9 is going to be negative 18 sine of 3t. Does that equal 0? Well, maybe for certain t values, but not for all t values. Negative 18, I should say. So because this is not true for all t values, that's a no. It doesn't solve the equation. So since it's not a solution, this is actually the answer choice we were looking for. Presumably, if we tried these other ones out, they would all come out the same on both sides of the differential equation. On this problem, we want to know which of these answer choices is the particular solution to this differential equation with initial condition y of 1 equals 3. Now, if you're wondering how you're possibly supposed to take this antiderivative, the short answer is there's really no way to do it, at least not using any of the techniques we would have. So the next fallback then is to just try taking the derivative of all of these answer choices and plugging 1 into all of them until you get something that matches these criteria that they've given us. So we have to have a function whose derivative is the square root of x to the 9th plus 1. Let's start there. So for this first one, using the power rule, we have 3/2 times 2/3, which just cancels out, and we have a 1/2 exponent. So we have x to the 9th plus 1 to the 1/2 power, which is great. But now we're multiplying by the derivative of x to the 9th plus 1, which is 9x squared, or 9x to the 8th, and that's not so great. That definitely does not match the derivative that they were supposed to give us here. So this is a no right away because the derivative doesn't match. Let's go on to the next one. This one, yeah. I mean, I could probably do this given enough time, but let's just come back to this one because if I find the answer choice quickly down here, there's no reason to bother messing around with this one. So both of these are kind of interesting because you have integrals with an upper limit that's x. So these are ones when you take the derivative, you're just going to use the fundamental theorem. And these 3's out in front, these are constants, so those are both going to be 0. So here we're just going to be plugging x in for the dummy variable, giving us x, square root of x to the 9th plus 1, and same thing down here. So C and D both have the dy over dx that we were looking for. Okay, well, that's not the whole story. We need one that when I plug 1 in for x, I get back a value of 3. They can't both give me that. So let's try each of them here. So if I plug 1 in for x in choice C, I've got 3 plus the integral from 0 to 1 of all this stuff. And now I have to somehow figure out a way to take the antiderivative of this, which kind of brings me back to my initial problem in the very beginning, which was I don't know the antiderivative of square root of x to the 9th plus 1. So I don't really know what this comes out to. I'm going to leave that for later. Let me try this last one out. This is kind of like my Hail Mary here. Hopefully this works. So this one down here, we would have 3 plus the integral from 1 to 1 of square root of t to the 9th plus 1 dt. And this one is a little more doable. Again, I don't know the antiderivative of radical t to the 9th plus 1. However, it doesn't matter because when you have an integral whose upper and lower limit are the same, it's basically an empty integral. There's no area there because you're not really taking the area over any length of space. So this is just going to be 3 plus 0, which comes out to 3, which is what we wanted. So it ends up being choice D, and thankfully we don't have to go back and test out choice B.